All right. Okay, so last class we continued with our discussion of stratified random sampling. And the first example that we looked at was an example where we computed the estimate of the population proportion based off of the stratified approach. So that example is given on slide 16. And from this example, what we can see is that the stratified estimator of a population value, so in this case, the proportion, but we can also use stratification to estimate the mean or the total, is effectively just a weighted average or a weighted estimation technique where you take the true strata proportions, which is capital NH divided by capital N, and you multiply that by the estimate that comes out of each of the different strata samples. So you can see, for example, here we have 0.171 multiplied by the estimate from the first strata, multiplied by 0.097, multiplied by the estimate from the second strata, multiplied by 0.726, multiplied by the estimate from the third strata. So in each case, these values are the WH from the strata, and these are capital W. So these represent the, we can call them the population allocation, or the true proportion of observations that belong to each strata. And then here we are simply multiplying by the estimate that comes out of each of the different strata. So from the samples. And this is the same approach that we take with all of our stratified estimators. So the idea when we are utilizing stratification is simply to break the to break the population into different groups. In this example, we have 3 groups, and to weight the estimates that come out of each group by the true proportion of observations that belong to each of those groups. And then the variance estimate works out to be pretty much exactly the same as the SRS estimate, except that we have to break it up by the groups again. So you can see that when we compare, or when we compute the variance of pi hat here, you have those same leading coefficients. So the W1, the W2, and the W3. But then here, inside each of these, this is just the SRS estimator for the variance of the estimator for pi, right? So this part here is really just variance of pi hat from SRS. So there's a lot of overlap between how the stratified approach works and how the SRS approach works. And going back to one of the initial points that I was trying to make when we first started studying the simple random sampling approach, effectively what we're doing here is we're just taking the idea of simple random sampling and we're breaking it up into different groups, and then we're combining the estimates from each group together to form one overall estimate. So we have SRS estimates within each of the strata, and then we have an overall estimate for the population quantity based off of that from each of the strata. Okay, so where we left off last class was extending on this idea. Okay, so we said, all right, well, how do we know when the variance of our stratified estimator? No, so the pi hat represents estimate from the population, and the pi tilde would be the formula to compute the estimate of pi hat. So pi tilde is the estimator and pi hat is the estimate. Okay, so last class, we left off looking at a comparison between the stratified estimator of the variance and the SRS estimator of the variance. So the purpose of this exercise is to try and gain some insight into how we can compare the two approaches, or more specifically, how can we compare the estimator that we would receive from stratified sampling to the estimator that we would receive from SRS, so from simple random sampling. And the goal is to say which one is better or more efficient. Now, with stratified sampling, a complication in comparing the approaches arises because there are different ways that we can allocate the observations to each of the different strata. Okay, so for example here, we're using, so in this part right here where I have little nh over n, this is under the idea of what is called proportional allocation. So proportional allocation says take the number of observations that are within each of the strata and divide by the total number of values. Okay. So from the previous slide, we can actually see mathematically what this means. So here we have capital NH over capital N, and then we would have the exact same proportion of values within each of the strata as it relates to the sample. So what I mean there is simply that if you have capital N total observations, and then capital N subscript H of them are within each of the sample, proportional allocation will simply allocate the number of total observations in the sample to each of the different strata. So capital WH, which represents the allocation fraction, if you will, so the amount of the population values that are in each of the strata, we assume that the sample is divided in the same way. So the proportion of observations from the sample that belong to strata 1 is equivalent to the proportion of observations from the population that belong to strata 1, etc. So right now what we're doing is we're assuming that this is how the observations were allocated to each strata, because we want to make a comparison between the simple random sampling approach and the stratified approach. But to do that, we have to know how the observations have been allocated to the strata. Right, so if we assume proportional allocation, that allows us to make some nice simplifications to our formula here. So again, you can see that the WH breaks up into WH multiplied by little nh over n. And this is only allowed because we are assuming proportional allocation. So this is only because we assume proportional allocation. Okay. Can I fit this over here? Okay, so this gives us an estimate of the variation of the estimator for mu based off the stratified approach that's equal to 1 over little n multiplied by a finite population correction times the weighted sum of the variances. So again, you can see that under this approach, the stratified estimator is not that different from the SRS estimator. We've just broken our population up into groups, and we are simply weighting the different values that we would get from each of the strata using the true proportions of observations allocated to each of the strata. Okay, so when we want to compare the estimators from SRS to the estimators from the stratified approach, one of the natural ways for us to do this in the context of a statistical comparison is to compare their variations. So we can say that one approach will be more effective than the other if the variation of that estimate is less than the variation of the other estimate. So in this particular example, we want to compare the stratified sampling estimator of the mean to the SRS estimator of the mean. So to compare them, we want to compare the variance of the estimator for simple random sampling to the variance of the estimator for stratified sampling. So on the line below question 1 here, I have for SRS, we have that the variance of the estimator for mu is equal to 1 over n multiplied by the finite population correction multiplied by sigma squared. Okay, so this is just the formula that we had already developed for the variance of the estimator under SRS. So we can see that if we compare what we have derived above under proportional allocation, okay, so if we compare we can call this equation 1 to equation 2, okay, that these formula are effectively identical. So they both have the same leading constant. So they both have 1 over n multiplied by the finite population correction. And then in the stratified approach, we have the sum across all strata of WH multiplied by sigma squared H. And then in the SRS approach, we just have sigma squared. So the only difference between the two approaches is the weighted variance from each strata versus the overall variance across all observations in the population. So therefore, if the more efficient approach or the better approach, depending on how you want to think about it, is the one with the lower variation, then we can show that the stratified estimator will be more efficient whenever the sum of the weighted variances is less than the overall variance for the entire study. Okay, so that's the main result from a direct comparison of the two. Now we can gain a little more insight into this approach by further decomposing these terms. Okay. This is okay. So we can gain more insights into this comparison by further decomposing these terms. Or rather, sorry, by further decomposing the population variance. Okay. So I'll start that here. Okay, so the population variance, so we'll take n minus 1 multiplied by sigma squared. Okay, so in the terms of the stratified estimator, this will give us the sum from little h to capital H multiplied by the sum from j equals 1 to little nh of yhj or yjh minus mu squared. Okay. We can write this as the sum from h equals 1 to capital H of the sum j equals 1 to little nh of yhj minus mu h plus mu h minus mu squared. So you can see here I'm just adding and subtracting 0. Okay, now we can complete the square, or we can expand the quadratic rather. And in doing that, we will have yhj minus mu h squared plus 2 yhj minus mu h yhj minus mu h plus mu h minus mu squared. All right. Okay, so this will give us the sum from little h equals 1 to capital H of capital N H minus 1 multiplied by sigma H squared plus 2 times the sum from H equals 1 to little h of mu H minus mu multiplied by the sum j equals 1 to little nh yhj minus mu h plus the sum h equals 1 to capital H little nh mu h minus mu squared. Okay. So we can show that this part here is going to go to 0. And then we can say this leads to sigma squared is equal to the sum from h equals 1 to capital H of n h minus 1 divided by n minus 1 multiplied by sigma squared h plus the sum h equals 1 to capital H of nh divided by n minus 1 multiplied by mu h minus mu squared. Okay, and then we can say that sigma squared, therefore, is approximately the sum from h equals 1 to capital H of wh mu h minus mu squared plus the sum of h equals 1 to capital H of wh times sigma h squared. Okay. So therefore, we can then say, so therefore, the difference between the variance of mu tilde strat and the variance of mu tilde is proportional to wh to the sum h equals 1 to capital H of wh mu h minus mu squared. Okay, and then this is actually important because we can then say that this suggests that so this suggests that if the strata have different means and small within strata variation, so I just need a little bit more room here. then variance mu tilde strat will be less than the variance of mu tilde. Okay. All right, so just to recap this, what we have determined in the first part of today's discussion is the difference between the we have drawn a direct comparison, small within strata variation. So kind of like the same thing as small within group variation. Okay, so the first thing we did today is essentially just show directly how we can compare the variance of a stratified estimator to the variance of a simple random sample estimator. In this particular case, we're focused on the mean, but we know that the totals, like estimates of the total, are the same. They're just multiplied by a constant. So those constants are just going to cancel out anyways. And we can basically derive the same type of understanding or the same sort of results using proportion estimates as well. It's just that those are going to be influenced by the estimate of pi hat h. So we showed directly that the variance of the SRS estimator or the variance of the stratified estimator will be smaller than the variance of the SRS estimator when the weighted sum of the variances across the strata is less than the overall variance. So that's the first result, which is shown here. So that would be the first result. But then we just took it a step further and we said, okay, this is helpful. Like, it's good to know when it would be less, but when can we expect this to be the case? So we would expect this to be the case when we have strata that are well defined. And what we mean by being well defined is that we have separate groups of observations that each have their own mean. And the variation within the strata is tight, which means that everything is relatively close to that average estimate coming out of the strata. And this is sort of the same idea as when you would expect to see rejection of an ANOVA null hypothesis. So we know that effectively we reject an ANOVA null hypothesis when the between group variation, so the distance between the groups, is much larger than the distance between observations within a group. So if you have three really well separated groups, but those groups are tight together, that should lead to rejection of the null hypothesis of an ANOVA, which basically just says that we have three separate means. So what we are showing here is that the stratified approach is going to work best when we have well-defined strata, H well-defined strata, and the variance within each of those strata is really close together. And from a practical standpoint, this makes sense because we are saying if all of the observations within the strata produce a small variation, then they're all very similar to each other, which means that the estimates we get from the strata should be quite reliable. So we've collected, in some sense, a representative sample within the strata, since all the observations are very similar. And therefore, we can take that approach and use it to build an overall estimate instead of trying to sample across the entire population at once. Okay. There's supposed to be like motion sensor lights in here, but it doesn't seem to work very well. They should have, oh, sorry. They should have controls on this thing. Okay, so the next thing we're going to talk about is constructing strata. And this is a fairly in-depth conversation, or we will have to have a fairly in-depth conversation where we discuss a number of different approaches to constructing strata within a a sampling strategy. And the reason that we would have to discuss different, or this, the reason why this conversation isn't a direct, here's the calculation for little n, is because there are different ways to allocate the observations to each of the strata. So effectively, the goal here is more or less compute optimal sample size given some bound. So we'll look at methods for doing that. And then given the computation of that optimal sample size via whatever the bound is you want to put on your error of estimation, allocate the observations into each of the strata. Now, we've already discussed briefly one way of doing that, which is via proportional allocation. So proportional allocation is the easiest way to allocate observations into the strata. It basically just says compute the sample size that you require for the particular experiment, and then use the true proportion of population observations within the strata to determine what proportion of your sample has to go into each of the strata. Okay. Okay, so when we allocate observations into a strata, there are a number of different things that we have to consider. So for example, we can consider the total number of elements in each stratum, the variability of the observations within the stratum, and the cost of obtaining an observation for each strata. Okay, so herein, we'll let little ph represent the cost for each observation going into the strata. So basically what we're saying here is that in some designs, there's going to be a certain cost associated with collecting information from each observation. So we can factor that into our calculation for the allocation of the observations. Okay, so as I mentioned briefly, the starting point here is more or less the same as, is pretty much the same as it was with SRS. We have to figure out how many observations we need in total for the experiment. Okay, so once we know the number of observations that we need for the experiment, we can then compute how many of those observations we want to allocate to each strata. And again, there's different ways that we can do this. So we've already seen proportional allocation, but we can also do things like optimal allocation, which is the same as name and allocation, I believe. But you'll see an example of that in a minute. Okay, so the starting point is the same as with simple random sampling. So step 1, determine number of observations needed for study. All right. So the starting point here is the same as the starting point in any type of sample size calculation that we have seen. Okay, so let capital B equal our Z alpha over 2 value multiplied by the variance of mu tilde strat. Okay, so we're just trying to solve for n, is the point. Okay. All right, so we know that the variance of mu tilde strat is equal to the sum from h equals 1 to capital H of little nh of WH squared multiplied by 1 minus, or I'll just write it. So we're going to have here, I'm just going to remove, so we'll start off just by squaring. So we're going to have B squared divided by Z alpha over 2 squared. And this is going to be equal to the sum from H equals 1 to capital H. Okay, now inside, the first thing that we have inside the sum is the WH squared, right? So we'll just write this as little nh over capital N squared. And the reason why I'm writing it that way will be clear in a moment. Multiplied by the finite population correction, which is multiplied by sigma squared h over little nh. All right, so now we can further simplify this. So the first thing that we can do is we can pull out that n squared term in the denominator of the first term in the sum. So the n squared term is not actually affected by the summation. So we can show here that this thing, if we multiply both sides by capital N squared, we have Z alpha over 2 squared. Okay, and then this thing is going to be the sum from H equals 1 to capital H of NH squared multiplied by sigma squared H divided by little nh minus nh squared multiplied by little nh multiplied by sigma squared H divided by capital NH minus little n H. I'm not using H for stratas next time because I cannot properly differentiate between H's and N's. Right. Okay, so same type of problem that we've seen before. Okay, so if you compare what we're doing here to what we did in lecture set 2 when we computed sample size for the simple random sampling case, this is the same process. We're simply taking the bound for our error, the bound that we desire on our confidence interval, we're setting it equal to the margin of error, and then we're solving for little n to try and achieve that optimal bound. Okay, so from this point forward, we just have to do a little bit of rearranging and we'll end up with an expression for little n. It's not the prettiest expression you're ever going to see, but it gives us something to work with anyways. Okay, so then what we can write below here is that that leading sum, H equals 1 to capital H. Oh, and sorry, this whole thing. Actually, I'll just write it like this, sorry. Just so that it's clear, because they still have the summations in front. Okay, so then we're going to have here NH squared sigma H squared divided by, and then we're going to use a little trick and go WH multiplied by N. Okay, and this is equal to the sum, let me just make sure, yeah. And this is a little w here, just so we're clear, not capital W, so this is little WH times N. Okay, and then this is going to be equal to the bound squared N squared over Z alpha over 2 squared plus the sum from H equals 1 to capital H of N H sigma squared H. Okay, so now we have a little n in the numerator here. So then we can say 1 over little n, or actually, I'll just go to the end. So then we can say little n is equal to, and inside here, we're going to have b squared n squared divided by Z alpha over 2 squared plus the sum from H equals 1 to capital H and H sigma squared H. And this whole thing is going to be divided by the sum from H equals 1 to H of NH squared sigma squared H divided by little WH. And then we need to inverse that entire quantity. So as I said, it's not the prettiest calculation in the world, but if you compare it to what we did for the SRS approach, it's actually it's pretty much equivalent. The only difference is that we have a weighted sum of the variances within the numerator and denominator of the expression. All right, so once we have computed the sample size for the entire experiment, now what we have to do is allocate the observations, or we have to determine essentially the sample size for each strata. So we have the overall sample size for the entire experiment, and we want to know how many observations do we have to collect in each strata. So to do this, what we basically do is multiply little n by a fraction, where the fraction has to sum to 1 across all of the strata. Okay, so for example here, and there's different ways of doing this. So for example, if pH varies across each of the different strata, and as a reminder here, the pH is unit cost per strata. Okay, so if little pH varies across the strata, one way that we can figure out how many observations to collect within each strata is to use the allocation formula that's shown on slide 24. So here we would have little nh, the number of observations, the sampled number of observations within each strata is equal to little n overall sample size multiplied by a subscript h, where a subscript h is just a ratio of nh multiplied by sigma h divided by the square root of the cost over the sum. Okay, so this is a fairly simple expression, and it's just the proportion of the sample size, the proportion of the population within each strata multiplied by the variance within the strata divided by the square root of the cost per observation in each of the strata. Okay, so this is one method that we can use to find optimal sample size and then to allocate the observations into each of the different strata. So I have an example of how this would work on slide 25. So in this illustration, we're saying we're going to use a stratified approach to collect information from 1 rural and 2 urban areas in Saskatchewan. The cost for collecting an observation from the urban areas are $5 a piece, whereas the cost of collecting an observation from the rural area is $10. For each urban area, the variances are 25 and 100, and for the rural area, the variance is equal to 225. All right, so again, the formula is a bit complicated, I suppose, but the approach that we are taking here will be this is basically just to follow the formula that are given above to calculate little n. So we're just plugging in the different pieces of information that we have. So the cost, the population size, and the variation. You can see that I have a very specific bound here. So L equals 0.9604. So this L, we can just think of this as capital B because that's the notation I've been using. And the purpose of the exercise is just to show how the formula on the previous slide would work. So basically, compute overall sample size for the entire experiment and then allocate that sample size into each of the different strata. On assignment 2, we're actually starting from the second stage here. So we're already given sample size, and then we're asked to allocate the sample into, or to determine the proportion of observations that would belong to each of the different samples under proportional allocation. So in the case of proportional allocation, the little AH, those are just capital NH divided by N, right? So that would be the simplest way of allocating. You're just allocating observations based off of the actual stratified weight, if you will. So based off of the WH. Right. Now you'll notice so like usual, when we compute the sample size, we always round up. So we have here, for example, 196.113 once we solve for each of these terms, and then we round up to 197. But you'll notice that when we compute the strata sample sizes, we round appropriately because each of the strata values have to equal n. So we only need to round up for overall sample size. Once we have the overall sample size, we'll achieve our bound for the experiment. And then within each of the strata, we simply have to round as we usually would so that we can obtain whole numbers that would add to the total. So it wouldn't make sense to have n1, n2, n3 that don't add to little n in this case. All right. Okay, so this illustration shows how we would compute sample size and how we would allocate the observations when we have a cost associated with each of the different values in each of the strata. Now, the more realistic or usually what will happen is the cost associated with collecting the observations will be unknown. I shouldn't say usually. The second case that we'll consider is the case where the cost associated with collecting each of the observations within the strata is unknown. So in this particular case, what we typically do is we assume they are equal. Now, this might not be a realistic assumption. I recognize that, but that's how we would approach the problem. So we have, in the situation where we assume cost is equal, then we want to allocate the total sample size into each of the strata using the same approach that we had before. So we basically want to minimize the variance of mu tilde st, or we want to find the optimal sample size to obtain the bound that we have that is of interest to us. Okay, so to do this, we can use an approach based off of Lagrange multiplier. So what we're trying to do here is find optimal sample size and allocation of the samples based off of equivalent cost for each of the strata that we are working with. All right, so to do this, I'll just start up here. Find little n1 to little nh given cost, which is p subscript h, is equivalent. So method. Okay, so what we're going to do is we're going to treat n1 to little nh as continuous variables. So we can use the method of, so we can use a Lagrange multiplier. So as was mentioned on the previous slide, when we assume that cost is equivalent, this problem of finding n1 to nh actually boils down to just finding the values of n1 to nh that minimize the variance of mu tilde strat. Okay, so if you think about, if you think back to calculus and what a derivative does, a derivative finds the minimum or the maximum points on some sort of curved object. Like if we think about a parabola, that's the easiest case because it only has one min or one max. I did that opposite, but one max or one min. And this situation is sort of like a multi-dimensional version of that problem. So we have n1 to nh, and we're looking for all of them that are going to minimize this object that we're going to assume has one global max and one global min. So we can, in an effort to minimize the variance of mu tilde st, we basically treat n1 to nh as being random variables or continuous variables. So those are like x in a standard derivative. And we're going to use a Lagrange multiplier to find the values of n1 and nh that minimize the variance of mu tilde st. So if you think about the surface of the variance of mu tilde st with respect to n1 to nh as kind of being, you know, like a bowl or something like that, we're trying to find the lowest part of the bowl. But it could be obviously in higher dimensions, like the bowl would just be a three-dimensional problem, so where we have three strata, but this could be for 4 or 5, 6, etc., different strata. Okay, so the setup here we require the critical points of little f is equal to n1 to nh multiplied by, or with respect to lambda, which is w1 squared 1 minus f1 multiplied by sigma 1 squared over n1 plus wh squared 1 minus little fh sigma h squared over little nh plus lambda n1. So I'm just going to move this over. Minus n. All right, so this thing is equivalent to 1 over w1 squared 1 over little n1 plus 1 over capital N1 sigma 1 squared over n1 plus wh squared 1 over nh plus 1 over capital NH sigma h squared over little nh plus lambda n1 plus nh minus n. Okay, so then take partial derivatives with respect to little nh and lambda. Okay, so we have d of f divided by d of little nh. This is going to give us negative wh squared sigma squared h divided by little nh squared plus lambda for h equals 1 to h, and df divided by d lambda is equal to n1 plus little nh minus n. All right, and then we set partial derivatives equal to 0. So then we get little nh is equal to wh sigma h divided by the square root of lambda h divided by the square root of lambda. Yeah, okay. And to solve for lambda, we write, okay, I'll do this, 949. Okay, so, and then the next thing we just have to do, I'll just write this down, this solution really quickly. So, and then to solve for lambda, we have n is equal to w1 sigma 1 plus wh sigma h divided by the square root of lambda. So lambda is equal to w1 sigma 1 plus wh sigma h over little n squared. Okay, and then real quick, so we can write under optimal allocation that little n h is equal to WH sigma h over W1 sigma 1 plus WH sigma h multiplied by n. Okay, so that is actually the last thing we need for the assignment too. Sorry, I went a little bit over time, but this is just what we just went through is the derivation of how you arrive at the allocation formula that's utilized for optimal allocation. So proportional allocation just says let capital NH over capital N be your little AH. Optimal allocation is just a ratio of WH of the weighted variance in each of the populations, which is a pretty logical approach to allocating observations to each of the strata. So in the last question on the assignment, you're basically just comparing the difference between what's given on slide 30 in terms of the allocation principle to what we would use for proportional allocation to show that the difference between the two is equal to what is given in the question on the assignment. Okay, so obviously I have to stop there. Sorry, I went a little bit over time. So on Friday, we'll continue to talk about optimal allocation. We'll go over this approach again, and then we're going to move into the last part of the lecture, which is basically some extensions of the stratified approach. And we will also talk about methods for picking the number of strata. So we have seen estimation under the stratified approach. We have seen now sample size calculation for stratified random sampling. We have talked about how to allocate observations to the strata. And the last thing that we really need to do, big picture wise, is determine how we would pick the number of strata for a particular experiment. And then from there, we can just talk about a few different extensions. So for example, double stratifying, post stratifying, this kind of idea. Okay, so that's it for today. If you have any questions, let me know, and I will talk to you guys on Friday morning.